Okay, logarithms. As I said, we just did exponentials, and so next logically would be logarithms, which helps you solve exponentials. In other words, a variable in the exponent. But as you notice, these first few examples do not have a variable in them at all. But that's because I want to kind of review some of the properties and some of the little tricks you can use when dealing with logarithms. And one thing I probably should state before we do that is the one I basically told you to remember. That, and it's easiest just to remember this one, that 2 to the third equals 8, correct? And then that's called exponential form because there's an exponent. All right? We could write it in logarithmic form and have it mean the same thing. Well, what is the base of 2 to the third equals 8? The base is 2, so the base of this logarithm will also be 2. Okay, that's what goes down there. Logarithms solve for exponents, and so this will equal 3, and it has to basically go right there. Okay, what this means, it means the same thing as that 2 to the third will equal 8. That's what logarithms do, is help you solve for that exponent. So if we were to look at this one, it is saying that 2 to some power would give me 21. But is that one that you know right off the top of your head? Is it one you could solve for, though? Yeah, if I gave you a calculator, it would do it right away. But that's, again, where I'm always afraid to do that, because then you're not really going to know what you're doing. You're just going to trust whatever number pops up on that calculator. And I have a problem with that. Okay. So what we can do is, let's say, because remember, before calculators, how did you have to do these? By hand, and you have to look them up in a big old book. Okay. Would have all these decimals on there. But they would only go from, say, log base 2 of, maybe 2 to maybe 10, and you'd have to work out and make it work. So here we have 21. I know log base 2 of 7, and does that make sense?
Was that on the report?
Now, does it make sense that 2 to that power would be 7? Because 2 to the second is 4, 2 to the third is 8, so 2 to that power being 7? Believable. How about this one? 2 to that power being 3? Believable. All right? And so what are we guessing here? Well, we're going to 21. So this is going to be between, well, 2 to the fourth is 16, 2 to the fifth is 32, right? So it should be somewhere between those two numbers. And what we're going to do is we're going to take a look at what we know. The only thing I'm going to give you is 7 and 3. Is there any way you can use 7 and 3 to get 21? Yeah, it's quite obvious, right? Go ahead, shout it out. Times 3. Do you agree? I've really just written the same problem. I haven't done anything different. I wrote the same problem. Now, if we look up here, though, at the product rule, it's saying if you have two numbers that are multiplied together in one logarithm, you are allowed legally to split those up into two logarithms and then just add them together. Notice how x is in one of them and y is in the other. That's because when you multiply bases, what would you always do to exponents? You would add them. You see how they go together? Multiply bases, add exponents. It's still the same thing. It just looks way different. So what we are allowed to do, if we want, is break this up. Notice the logs on it both times. Right? That's basically what this is saying, isn't it? We're allowed to do that. But then what do I have to put in between those two? I have to add them. Okay? Now, we just got lucky that those are the two that I gave you. I told you that log base 2 of 7 is 2.8074. So I get to replace that with 2.8074. And then I have to add whatever log base 2 of 3 is, which is 1.5850. And you remember in advanced math, this is before we did this one in there, I made you like add, subtract, decimals and stuff like that, and that was fun. Everybody remembered how to subtract decimals. That went really well. All right, so you add these together, and what do you get? $4.3924. Is that what you said? Yep. Now, was that what we said? We said 2 to the fourth was 16. 2 to the fifth is 32. Does that fall in the range where we thought this exponent was going to be? So 2 to that power being 21? Believable. Had we gotten an answer of 43, hopefully we would realize 2 to the 43rd power being 21? I don't think so. And that's the problem. Some students in some schools, they just write down 43.9. They just keep going. They don't even hesitate, you know, because they have no clue what that's saying. And you do. You know it's 2 to some power has to be 21. That makes sense. Okay. Now, this is a fraction. Do you agree that 7/3 is, you could write that as, say what, 2 1/3, right? So it's log base 2 of something has to be 2 1/3. So it's probably going to be really close to what number? 2 to the first, right? Because 2 to the first is 2, right? So it's not going to be too far from that, is it? We wouldn't expect it to be too far. Is there a question? Got it? Yeah, here we're dividing. And when we divided bases, what do we do with exponents? So look at the quotient rule. It's doing the same thing. It's saying if you divide those two numbers, you can split it up into two of them, but now you have to subtract. Now, in the product rule, did it really matter what order you wrote the numbers? No, because it's multiplying and adding, the two that have commutative properties. Now we're doing division and subtraction, the two that are not commutative, meaning you move them wherever you want. And so you have to be very careful. So maybe we'll do this in green so you can see the difference. So we can write it into two separate logs. And again, I'm kind of doing it as if this is how you would do it. You would write it into these two, and basically then you would go to that big book of tables, then you'd have to look these two up and then subtract them. Because obviously if they wrote every single logarithm possible, they'd never be done. You'd be writing forever. Okay? And again, you should maybe research how they actually did these by hand. It's kind of amazing. So any log base 2 of 7. Well, I know that's 2.8074. What I mean by hand is when they did the tables by hand. Somebody had to come up with them, and they did them by hand. Okay. Subtract. Well, what is log base 2 of 3? It's 1.5850. This is when things went a little haywire, when I just gave you these types of problems without calculators. No, that darn borrowing. 4 minus, actually the really ones were when you had to subtract the bigger number. That's when people struggled. Big. So 4 minus 0. 7 minus 5. Oh, you got to borrow. Becomes a 7, becomes a 10. 10 minus 8, 2. Now, is that believable? 2 to that power being something just a little bit more than 2. Yeah. Again, what if you've gotten 12? Now, really, 12 as an answer doesn't seem that big, does it? But 2 to the 12th is big, and it's nowhere near 7/3. Okay? So there you go. Now, these are the types that I know some of you did struggle on from time to time, because you always would look at, say, that number and try and use them. Okay, and that's a good idea. But realize that you also have any powers of those numbers. And you also have any power of 2. So you have a lot you can use. So, is any power of 2, right? Log base 2 of, say, 4 is pretty simple, right? I mean, 2 squared, right? So any powers of 2 are pretty straightforward. So is there any way that I can break this one up? And when I do it, okay, we got a 3 and we got a 7. I mean, do those go in there really well? Yeah. Okay, he jumped ahead a little bit there. Let me just kind of slow it down. Please keep in mind there's someone in here that has never seen these before. Okay? So take your time on that a little bit. I understand exactly what he said, but keep it in mind. I think we can all agree that 7 times 9 is definitely 63. All right? And why would you choose 7? Well, it's one of the options we have. And so now let's just break it apart and see what we can do. And then log base 2 of 9. So do we add, subtract? What do we do there? You're going to add because it's multiplication. It's this one, right? It gets broken up into addition. Well, one of those you know. One of them is just written right up there. It's 2.8074. So you can replace it. Plus, now this is a problem. There's a lot of ways you could do it at this step, but I'm trying to figure out what's going to be most beneficial here. I'll kind of show you both ways. Okay. Basically, what was said earlier is that this is really 9 is really 3 squared. Now, why would you want a 3? Well, we've got a 3, so that's why we want it. And the last rule that is really actually, if you remember, the biggest, it's the one that really allows us to solve these problems in the end, says if you have just one log and there's something up there in the power like that y is, see there's a y right there, it says you can actually just throw it right out front. Okay? Because when you did a power to a power, what did you do with exponents? You multiply. Okay? And that's really what you're doing. And so this 2 can actually just come right out front. So it's 2 times log base 2 of 3, which we know. Log base 2 of 3 is 1.5850. Okay? And then it becomes decimal work at that point. And then I'll just show you the other option. It comes down to the same decimals. Obviously, I'll show you the other option real quick. For log base 2 of 9, what some people do is they break it down again. Because 3 times 3 would be 9. And then just add it, but really just adding those two is the same thing as multiplying the decimal times 2. All right. Now that we're done with our fire drill, you end up with that one, and you get, according to my notes here, you get 5.9774. Now, does that make sense? 2 to that power, it's about 2 to the 6th power. Well, 2 to the 6th is actually 64, correct? And so 2 to the 5.9 actually makes sense, just a little short of 64. Okay. 5.9774. So, well, that's weird. Anyway, common logarithm is a logarithm with base 10. And basically, if you see a log that's written just like this with no base at all, you can assume a 10 goes in there. That's the base. And it's really hard to see, but that base right there is E. And E is a number, 2.71828, blah, blah, blah. Keeps going. It's a number that has been found in nature an amazing amount of times, okay? Which is why it's called the natural log, the opposite. And you can blame the French for it being ln and not nl, right? Because they say it in the opposite order in their language. So we are to solve each of these for y, which means get y all by itself. Well, right there's ln, which means natural log of y, equals 10. Again, you could look at that as saying log base e of y equals 10, or you can of y equals 10. But normally we don't write it that way. You just say natural log. Okay. And so what is the one thing that will cancel out log base e? Yeah. Or natural log. What's the one thing that'll cancel it out? And look at your calculator. Look at natural log. What's right above it? Yeah. Right above it is e to the x. So if I take e to that power, I do it on this side, that's my new base, and e to that power, that's some new algebra. All of a sudden that stuff just becomes exponents. That's interesting. All right. Now, e and log base e, what do they do to each other? They cancel because they have the same base. See, base e, gone. So in other words, y equals e to the 10th, which is a pretty big number, actually. And you can find that number if you want. I've got 22,026.5-ish. Okay. Now, if you were clever, you could have come up with that answer a little quicker. Because really it means natural log of what will equal 10? Well, natural log of e to the 10th, will that equal 10? Natural log, it's log base e of e to the 10th equals 10. So does it actually equal 10? Yeah, so that one was a little easier than that, but that's fine. What's different about the second one? Okay, it's an exponential form, and there's kind of that 2 hanging out. If I were you, I would get rid of the 2 before you try and do anything. So let's divide by 2. Because remember, again, you might not have looked at it this way, but a lot of times PEMDAS is order of operations, but if you do it backwards, that's really what you do in algebra. Do any adding and subtracting you can first, then any multiplying and dividing, then you take care of any exponents you can, and then you take care of any parentheses you can. It's really the opposite. Well, what's going to get rid of an e? A natural log. So if I take the natural, wow, helps if I don't write it right on the line. Natural log of this side, then I better take the natural log of that side. So it looks something like this, because they basically cancel each other out. Here, you can read that a whole lot better. No, you don't have to write it if you don't need to, because really what happens with the natural log and the e? They cancel. And again, that rule that brings this down to the front is really now really important because it brings it down to the same level. Or a lot of you just realize, kind of said it just kind of falls down. That's fine. But y is not by itself yet. Divide by 4. Now, if you're asked for the exact answer, well, natural log of 7.5 divided by 4, that's the exact answer. But a lot of times you want some kind of decimal. And what is that decimal? Point. Here's what I got. 0.5037 is what I got. Yes, make sure that you do, because natural log gives you a parenthesis, make sure you close them off. And then divide by 4. Okay? Now, these next couple have various ways you can do them. Can I erase what's up here or no? Good? Oh well. Let's try it again. There we go.
You needed the sound effect. Come on.
So 3 to some power has to be 7. Well, we can get a guess, right? Because 3 to the first is 3, 3 to the second is 9. So it's between 1 and 2 somewhere, right? 1 point something. Okay, so the problem is my variable's in a spot that we're not used to having variables. We're used to having variables on the same level as everything else, so we need to bring it down somehow. Okay, there's a lot of ways you could do this. Okay, I'll show you one way it could be done. We're going to take a log of both sides, but we're going to do log, what I would do is log base 3 of both sides, because then you have a 3 sitting right here and a y. You see that? If I do it to the left side, do you see perhaps why that might be a good strategy to take log base 3? Okay, because these will cancel because the bases are the same. But then if you take log base 3 of one side, you got to do it to the other side. So y is whatever log base 7 divided by log base 3 is, because remember that's what this means. That's how you have to type it into a calculator if you want it to actually give you the answer. Okay. You take log base 7 divided by log of 3. Do you take log of 7 divided by log of 3? That's how the calculator will solve it for you. So go ahead, why don't you do that? What is it? 1.7-ish. So let's go out a ways because these do have to be kind of accurate. Now, why do these have to be kind of accurate? Have you seen something like that recently? 3 to the y minus 7 maybe? Maybe something like that. They're exponential graphs, right? They change in a hurry. So is it important to be somewhat accurate with your number? Because it could make a big difference. Okay. Now, that's one way to do it. Another way that would have gotten you to the same one, and I was hoping somebody would say it. I mean, that's, well, yeah. That's exponential form, right? Can you write it in logarithmic form? Log base of 7 equals y. Doesn't that get you to that step a lot quicker? But that's why this works, is because of the work you just saw here. That's why that maneuver works. Okay? It just gets you there quicker. What base are we talking about on number 10? How do you know that? Yeah, there's nothing written there, so it's understood to be 10. Everybody good? So I can erase this? So there is an understood 10 right there. So is taking another logarithm really going to help me here all that much? Not really. So what you could do, though, is take 10, and make that the power, and then do the same thing over here, right? Because isn't that the opposite? Log base 10, which is the common log, is 10 to that power, right? You use the same base. Just like we did here, we use that same base. But why is that helpful? Because what can I do now? I can cross a whole bunch of stuff off. So y equals 10 to the 4.8 power, which is pretty big. Yeah, 63,095.73. See what I mean? That's a pretty small exponent, isn't it? But remember, exponentials just take off in your graphs. Now, I think I heard somebody whisper something as I was starting letter D. Perhaps I didn't. Of another possible way of doing that one. This is logarithmic form, correct? Write it in. What's the base? Where's the exponent? It's right there in logarithmic. I don't know why my equals is way up there, but it is. Yes. On the right side? What I'm doing is I'm taking this log base 10 that's there, and I'm making that the exponent with 10 as the base. So that's my exponent. So I have to do the same thing. I have to make that the exponent with 10 as the base. I have to do the same thing to both sides. These here, these two are there because I know they'll cancel because they have the same base. Just like on this one, I knew I needed the same base, so I basically did log base 3 of both sides. And the only reason I did log base 3 instead of log base 17 or log base 10 is because I knew that would happen. I set it up for that to happen. In these two right here, yes. For example, I could do what has to be down here for this to cancel? But really, I did the same thing to both sides. I made both sides the exponent and 10 the base on both sides. That's what I did. It's just on this side, it just canceled. There is no log base 10 on this side because there wasn't that one there originally, and I never added one in on the left side. I just took the one that existed and I put it as the exponent. Okay, I never created another one in the problem. In fact, I tried to get rid of all of them is what I was trying to do. Yep, the whole thing is the exponent. Yep. Okay. All right, I believe you're going to need, you're going to need some graphing calculators. Here, much better. All right. When we did all those exponentials, do you agree a lot of the exponentials either look like that, or the exponentials looked something like that, or, you know, actually, did any look like this one that you had? They did? Yeah. And some looked like this, right? Exponentials kind of did that kind of graph, correct? And logarithmic are very much related to them, but do you agree in all those exponentials there was almost always and it was horizontal, correct? Natural logs are kind of doing the inverse of exponentials, correct? Or any type of logarithm. So any anticipations here? There might very well be vertical asymptotes. Okay. So why don't you go ahead? Now this one's not too bad. I wrote it on the whiteboard just so that I can go to the calculator and type it in. So of course we want to check, make sure nobody's messing around with you. Check your mode. And y equals. Get that out of there. I don't want that. So 3. And then where is natural log on this thing? Well, n right about there, right? Notice again, it gives you that set of parentheses to begin with. So you have to be very careful when you decide to close those off. So use x minus 1, close them off, plus 2. And let's just zoom standard so we're all looking at the same thing. Huh. So this one just stops. So yeah, I think the calculator struggles because of what happens down there. It's not sure what's going on. It can't find that next point because remember, it only finds points every so often. And if it runs out of points, it'll struggle. So let's see what happens. Ooh, errors. Well, that's great. Okay. And so we'll work our way. Do we ever get any? Oh, whoop, there we got something. Now, okay, you can stop now. Okay, so apparently I've broken the calculator.
Just let it get to 2. Really impressed if it stops it.
That would have been pretty good, yeah. I would have been impressed as well. So now this is, again, you have to stop for a second and say, wait a minute. When we did exponentials, we knew we had horizontal. And you already told me you were expecting, seeing logarithms are kind of, you know, the inverse of that you were expecting some vertical. And so you have to ask, you know, what can we get, what can't we get? Because you know what I'm going to ask you for after you get this graph. You know that's what you're going to get. And so you have to decide, well, what's possible, what's not, right? So why don't you get a nice little sketch of that graph? Obviously, I don't expect you to graph 7 and 7.3753 perfectly, but just get something that looks like it, and you kind of know that there's an asymptote there already. Okay, but where is that asymptote is quite possibly the question. Because some people might have told me that the asymptote was at 2, but it's not. Okay, yeah, it's at 1. I'm looking at the graph. Because it's coming down like this. And actually, I know it's at 1 for other reasons. Yes?
Okay. I thought on the graph it sort of goes down farther than the line thingy, but when you look at the points, there's no negative.
Oh, you mean in the table? Okay, good question. Because remember, it does look every so often. So it did look at, say, 1.1 and 1.2, 1.4, or something along those lines. And that's where, so if you changed your table to go up, say, by 0.1, then you would see some negatives. If you start, you know, they're kind of in between 1 and 2 there is where all the negatives would be. Great observation. Good question. Okay. I want you to graph the actual graph and not what's necessarily shown on your calculator. Okay. Because I think we can all agree that that's not the graph. All right? We know for sure that just gone. But I think hopefully you know There's an asymptote there, and it is going to keep going. Okay. And here's the question. 1 is where it starts saying error, correct? We'll put 1 in here. Can you actually put 1 in is the question. So 1 minus 1 is?
0.
Natural log of 0 is saying e to some power giving you 0. Well, what about e to the 0?
1.
It's 1. Okay, so is this truly, just this, who cares about these? I mean, is this ever really going to say 0? Just this portion, that's never going to happen. Okay, or you can't even take the natural log of 0. Okay, you can take the natural log of 1, but you can't take the natural log of 0. And so that's why it's a problem. And this is basically telling you where the asymptote is. Isn't this line right here, x equals 1? Because it's basically where you have to stop putting them in. So you want to try some domain and range then? Who wanted to try? Yes. Now think back to all those exponentials. Remember that one worksheet we corrected? After about the second one, I got tired of reading one of the answers because it was always the same, correct? Which one was always the same? Domain, and what was it? It was always negative infinity. And this is the inverse, and look at which one's always going to be. It's range. And this is always the one where you're going to have to be dealing with the asymptotes. You see how they are inverses of each other. Okay. So what are you going to expect on letter B? Are you going to expect to get, you know, an asymptote? Yeah. And you might even be able to make a pretty good guess as where it's going to be. Let's find out. Is everybody done with this one? Just look at this one. Was this one at -1? No, this one was that +1, wasn't it? So now how do you type in that one, though? That's the interesting one. Everybody think they know? Yeah. Close. Yep. You always do log of the big one first and then log of the base. So we will do, yes. Okay. Do you get that there is an asymptote here, though? Okay. So as we go, say, this way, from left to right, the very first point we technically get is 1 point, infinite number of zeros, and then 1. Right, do you agree? 1.0, and just keep saying 0 for the rest of your life, and then say 1. Okay. So it's very, very close to here. Is actually the first x value that actually graphs something. So instead of saying that, we say from 1, not including 1, all the way to infinity. Because 1 actually never happens. Okay. That 1 doesn't happen? Okay, we know 1 doesn't happen because we tried putting it in here. 1 minus 1 is 0, and the natural log of 0. You're saying e to some power. That's what natural log means. It's e to some power is going to give me 0. Remember, e is like 2.718. Can you take that to a power and get me 0? No, you can't. Okay, so the natural log of 0 does not exist. Okay, and so when I put 1 in, I do not get a y value because right away it's undefined. It doesn't exist. Okay, when you put it in there. Okay. So how are we going to type this other one in? Well, we kind of were told. Do you hit natural log, though, for this next one? No, you hit the, what's it called again? Better than that. Come on. Well, I better clear this out screen. Common log of 1 minus x. How are you going to put it in? Yep, you divide by log of 2. It's the only way this calculator knows how to do any other log other than base 10 or e. It's the only way it knows how to do it. Everybody ready? Everybody's got it typed in? So what do you think? Is a TI-83, or whatever I have here, 84 plus, is that the actual graph? Ooh, but is it doing the best it can? Yeah, it's just as good as it can do. But once again, you can't put 1 in. Because if I try putting 1 in for x, it's 1 minus 1, which is 0. So you're saying 2 to some power gives me 0. Never going to happen. So 1 can't possibly be graphed. 1's not part of your domain, which is why, technically, there's an asymptote there, and it keeps on going. And so does that one. So as we go from left to right, again, domain left to right, what's the first point that we actually hit for next file? We do get negative infinity all the way to 1, but you can't include it because you can't put 1 in. 1 gives you something that you can't actually calculate. And range.
That's favorite.
Yes. Negative infinity to infinity, because that's bottom to top. Any questions?